Greetings, Monsieur Johnny. Glad to see you once again for this lunch. The fourth lunch already that you've been to. In fact, you've actually caught up on a lot of it already. All that's left is just equilibrium and acids and bases. So the past few days I've been teaching you about the mole concept, as well as stoichiometry, kind of dealing with how it's a foundational concept in chemistry and use it in a bunch of other units, and I'm showing you some example problems with conversions in the mole concept, and then with stoichiometry, kind of taking that step a bit further and showing how you can take a chemical reaction, and if you are given the amount of one element or compound in the reaction, you can find out the amount of another element or compound in the reaction. Well, today, in my opinion, this is actually my favorite concept in all of chemistry, and it is called dynamic chemical equilibrium. Absolutely a fascinating concept. Before, in your chemistry classes, in earlier chemistry classes, you might have dealt with chemical reactions that were as followed. A plus B yields AB, or AB yields A plus B. And that basically told you that if you combine A and B, it produces AB, and that's what you get. Or if you have AB, it decomposes to become A plus B. Now that is technically correct, but what if I told you that A and B in this reaction will combine again to form AB at the same time that AB decomposes to produce AB? Whoa! Whoa! Is your mind blown yet? That's absolutely fascinating. That A and B can decompose to become A and B, but at the same time A and B can combine to form AB. That is absolutely fascinating. And we denote this with an arrow pointing back that way to show that AB is decomposing to A plus B at the same time that A plus B is combining to form AB. I know I've just said AB 100 times. It'll become more clear when we work through kind of the key points within equilibrium, but that's essentially what it is. Instead of having a reaction that goes from reactants to products, you have a reaction that produces reactants and products at the same time at an equal rate. That's what equilibrium is. In fact, equilibrium is actually quite common around us in everyday life. You may have never even thought about this before, but when you really think about it, if you have reactants, the single arrow that way, where it only yields the products, only happens if 100% of the reactants combine or decompose to form the products. That's in an ideal or perfect world. How common do you think that's going to happen? Realistically, maybe 99.9% of this will combine to form AB, but 0.1% won't. It's not always going to be a perfect reaction, and in this case we get equilibrium, where not 100% of reactants will form 100% products. Maybe it'll be 99%, maybe it'll be 75%, etc. In fact, this is actually explored more in acids and bases, which we'll cover in another day. But for now, chemical equilibrium. One of my favorite concepts of all. It's absolutely fascinating. Now, before we get started, the best thing about equilibrium is that nothing changes. It's crazy to think about, isn't it? Even though what I just told you, a reaction can go forward and backward at the same time, but to your eye, nothing will change. Nothing will change. This is all at the microscopic level. Things around you, reactions are going backward and forward at the same time, but you don't even notice it. Nothing's changing. It looks constant. Okay, now, I have this information sheet in front of me, and I will kind of go over some of the points of equilibrium, go through it before we go through just some example problems. Okay, so equilibrium happens when a chemical reaction does not convert all reactants to products. Many reactions reach a state of balance or dynamic chemical equilibrium, in which both reactants and products are present. So this balance basically refers to dynamic chemical equilibrium. So a system is at equilibrium when the forward and reverse rates of a reaction occur equally. So as you can see here. So if AB is equally decomposing to form A plus B, at the same time A plus B are combining to form AB, if that's happening at an equal rate, we are at equilibrium. Another thing to keep in mind, it doesn't mean reactants and products are present in equal amounts. It means that the reaction has reached a point where the concentrations of the reactant and product are unchanging with time, since the forward and backward reactions have the same rate. So the concentration of AB in this example could be 1 mole per liter, and the concentrations of A and B individually might be 0.1 moles per liter. It doesn't matter even if it's 95% reactants or 95% products. What matters is if it's decomposing and combining at an equal rate. That's essentially what equilibrium is. So as I discussed earlier, it's denoted by this symbol, basically 2 arrows, one going forward and one going backward. And here's a common example in everyday life. Sodium chloride in equilibrium or decomposing to become sodium ions and chlorine ions. Although you might think nothing much is happening at the molecular level, there is constant activity because the sodium chloride is constantly dissolving as well as precipitating. This is easy to see if you dissolve table salt in water. That's if you have a large amount of table salt. It may appear nothing's happening, but the ions are constantly dissolving as well as precipitating, although you might not see this. It may look constant, and that's the thing that's fascinating about equilibrium. If temperature is constant, equilibrium will be reached so that for every sodium chloride ion, or every sodium chloride that dissolves, another will precipitate. So if temperature is constant, equilibrium will be reached. But if temperature is adjusted, the system will try to get back to its equilibrium state. But if there's a stress that's put onto the system, it will try to get back to equilibrium. And that's where we actually have Le Chatelier's principle right here. A system at equilibrium, so we can take this system right here, subjected to a stress. I'll go over stress examples on the next page of this. Will shift to try and minimize the change caused by the stress. This is caused by a change to the system that makes the forward and reverse rates of a reaction no longer being equal. So for example, the one I just went over was temperature. But there's also concentration, pressure, or volume. Those are the 4 main ones. So we can go over those real quickly. Before I go over the different types of stresses, I was actually researching some chemistry the other day, some jokes. Well, I was researching some facts on acids and bases, right? And I came across this joke, and I honestly have no idea what it is, Johnny. So if you have an idea what this means, I might be clueless or dumb. I have no idea what this means. You can tell me. Just hop onto the comments and tell me what it means, because I have no idea what it means. How can you spot a chemist in the bathroom? Okay, so I have no idea what the answer to this is, but apparently, it is they wash their hands before they use the toilet. That's how you spot a chemist in the bathroom. That is absolutely bizarre to me. It makes absolutely no sense. So if you know what that means, please tell me, because I am absolutely clueless. And I went upon that the other day. I'm like, wow, I do not get it. I must be missing something. Anyways, back to the equilibrium. Okay, so as I just discussed in Le Chatelier's principle, a system at equilibrium subjected to a stress, which I'll go over right now, will shift to try and minimize the change caused by the stress. The first one is concentration. If a species basically refers to a reactant or product in a reaction. So for example, the sodium chloride decomposes to become sodium ions and chlorine ions. A species could be like Na+. It would also be Cl-, or it would be NaCl. A species is a single component of a reaction. So if a species concentration, and actually concentration, I should quickly remind you again what it is. Concentration simply refers to the moles of a substance per liter, which I actually briefly went over in stoichiometry, I think. So let's say you have, and it's written with a capital M, or it's in square brackets. It can be written as an M or in square brackets of that substance. That's what concentration is. So if you have 200 moles per liter, that would be 200 M. And yeah, that's basically what concentration is. The amount of moles of a substance there is per liter of that substance. So yeah, so if this concentration is lower, the equilibrium will shift towards that side of the reaction to increase the concentration. But if it's raised, so if one of these is raised, the equilibrium will shift away from that side of the reaction to decrease the concentration. This is definitely a very confusing concept at first, and it took me a while to understand it, but I'll get to an example problem later on that makes things more clear. Next, if we go to pressure, pressure is basically the amount of space that gas molecules, okay, pressure only refers to gas. Molecules don't use pressure for liquids or solids. Pressure is essentially the space that gas molecules have between one another. So if pressure is high, that means there's a small amount of space and the particles, or the gas particles are rapidly moving and hitting each other. If a pressure is low, then it means there's a lot of space and the gas molecules aren't colliding as frequently. So if one side's pressure is lowered, the equilibrium will shift towards that side to raise the pressure again. But if pressure is raised, the equilibrium will shift away from that side to lower the pressure. Volume is a reciprocal with pressure, so it's essentially the opposite. As volume increases, pressure decreases, so it's the exact opposite as pressure. Now with temperature, one thing I actually didn't include, but technically they are included in reactions. There is an energy term in these reactions. I'll go over it in examples, but as temperature increases, it will cause a shift away from the energy term to consume energy. So this is dealing with endothermic and exothermic reactions. A decrease in temperature will cause a shift towards the energy term to produce more energy. Okay, so I'll get to an example problem here, dealing with stresses. Question number 1. What conditions favor the production of large amounts of ammonia? So ammonia is this right here. One second, let me just get my pen. Okay, right there. That's ammonia. And this is the energy term, by the way, kJ, 92 kJ. That's the energy term. I'll just point that out. Energy term. Okay, so we're trying to get a lot of ammonia. So when we looked at shifts, we looked at concentration, pressure, volume, and temperature. And if we lower or raise it, it will cause the equilibrium to shift. What the equilibrium shifting means, essentially, when the equilibrium shifts towards a certain side, it will favor that side to try and produce more of it. If it shifts away from a side, then it will try to produce less of that. Element or compound. So in this case, we want to produce a lot of ammonia in this reaction. So So we have nitrogen gas and hydrogen gas. And we want to produce a lot of ammonia. So as I just said, we want the equilibrium to shift towards ammonia, because as equilibrium shifts towards a side, it produces more of it. So we want there to be a shift this way to the right. So how do we do that? Well, we would have a, let's see here, we can see an energy term here. So with temperature, we lower it, because if we lower temperature, the equilibrium will shift towards the side to increase it again. So we could lower the temperature. That's one. What else could we do? We could have, now with pressure, you basically have to count the gas molecules on each side and look at the coefficient, right? So we can see all of these are gases, right? We see coefficient of 2, so there's 2 gas molecules on this side. And on this side, there's 2 different species. This one is a coefficient of 3. This one is a coefficient of 1. 3 plus 1 is 4 gas molecules on this side, 2 gas molecules on that side. So we can see that this side has a higher pressure. So since this side has a higher pressure, we would want to increase the pressure of this side so that the equilibrium shifts towards this side to produce more ammonia. High pressure. And another thing we can also do is deal with concentration. We could simply decrease the concentration of ammonia, or we could increase the concentration of these gases to cause the equilibrium to shift towards ammonia. But these are the 2 main ones. However, if you know kinetics, you know that high temperatures increase the rate of a reaction. But in this case, we want a low temperature to produce a large amount of ammonia. Well, maybe we can have a high temperature to increase the rate of the reaction, but continuously remove ammonia to drive the reaction forward, because removing ammonia deals with concentration. So low temperature means the reaction will be slow, right? But we want to get large amounts of ammonia. So if we have a high temperature, but remove ammonia continuously throughout the reaction, that'll cause the concentration of ammonia to be lowered and cause the equilibrium to shift towards the ammonia. So that's another one. Lower concentration of ammonia. Again, I don't want to take up too long of your time, but that is essentially the idea of Le Chatelier's principle. Don't have too much time left for the remainder of lunch, so let's just go over the last key points. Okay, so now we have the equilibrium expression. So we have this mathematical model. So we have this, let's say we have this reaction, A plus B yields C plus D, and it's at equilibrium. So to figure out a equilibrium constant, KEQ, we have this expression. The concentration of species C raised to the power of its coefficient times the species concentration of D raised to its coefficient, divide that by the species concentration of A raised to its coefficient, multiply it by the species concentration of B raised to its coefficient. That, if you type that into your calculator, give you KEQ, which is a constant. Now, if KEQ is greater than 1, the forward reaction is favored. If the forward reaction is favored, it'll want to go this way, so following this arrow, it will want to produce more products. If KEQ is equal to 1, the forward and reverse reaction rates are favored equally. If KEQ is less than 1, the reverse reaction is favored, so this arrow, and it will want to produce more reactants. And that deals with shifts, so that can tell you where the equilibrium is, if it's trying to produce more products or more reactants, or if it's at the same. Okay, and one quick thing to keep in mind, only gases and aqueous solutions are put into this, no solids or liquids. So let's say B was a solid, you'd omit that, and you'd only put this into your calculator. Okay, so let's get into some example problems. 1.00 molar, which is concentration, of ammonia was placed in a 1 liter container. After some time, the concentration of hydrogen equals 1.35 molar and was not changing. What is the value of KEQ? So, as we just saw, KEQ equals that. So let's label each of these. So in this case, we actually only have, well, we do have two products, but we don't put the energy term into the equation. So we will treat this as A, B, and this will be C. And there will not be a D. So we will put NH3 at the top. Okay. Let's check this. Yeah, okay. So when we're dealing with these questions, we want to create something called an ICE table, which is initial concentration, the change in concentration, and the equilibrium concentration. So let's just draw that right there. And then we would write down each species. So we have N2, and then we have, what else do we have? H2. I should draw square brackets because square brackets also represents concentration, and then we have NH3. These are the reactants, so these are A and B, and that'll be C. So these will be in the denominator, that would be in the numerator. So we start with 1.0 molar of NH3, 1.00 m. However, although we're not told the initial concentrations of this, it's assumed that this is 0. We start with none of that because we start with this, and then it reacts, or it decomposes to become this, and it becomes an equilibrium. So after some time, the concentration of H2 was 1.35 molar. So it's assumed that's at equilibrium. So the change is plus 1.35 m. Notice how we have a coefficient of 3 in front of the H2, 1 in front of the N2, and 2 in front of the NH3. So we figured out that the coefficient, or a number raised to the power of 3, equals 1.35 m. Right, so we can actually just simply, since this is a coefficient of 3, we can simply take 1.35 divided by 3 to get 0.45 m. 0.4. Yeah. So since the concentration of hydrogen is a number raised to the third power, it's multiplied by itself 3 times, it'll be 3 times as large as nitrogen. So we can take that number, divide by 3, and the final concentration of nitrogen would be 0.45 m. So the change is plus 0.45. Because the coefficient is 1 there, coefficient of hydrogen is 3, so it'll be 3 times as great a change. Now for NH3, because this is initially at 0 and this is at 1, this value has to decrease, because if this increased, then we'd still have 0 of that. If this decreases, some of that initial concentration becomes that. Coefficient here is 2, so we can just take 0.45 and multiply that by 2 times 2 equals 0.90 minus 0.90 m, sure, m. And then the final would be 0.10 m. So those are the final concentrations, and as you can see, as I discussed at one time earlier, the concentrations do not have to be equal. They just have to be changing at equal amounts. Now that we have the equilibrium concentrations, we can perform this into our expression. So we have C is NH3. So we have the concentration of NH3, which is 0.10 m. Yeah, 0.10 m raised to the power of 2, because the coefficient is the power. And then we take these numbers, we have concentration of 0.45, but we don't have a power, so we just leave that as is. And we have 1.35 raised to the third power. Type that into the calculator, that will give us a KEQ value, because KEQ equals that. Give us a KEQ of, let's see here, 9.03 times 10 to the power of -3. That will be our KEQ value. Okay, last question. Now these questions might be somewhat challenging and tricky, but with more and more practice, you get used to them a lot quicker. Okay. So initially, the concentration of hydrogen equals the concentration of iodine, and they're both 0.75 molarity. The system is allowed to reach equilibrium. What are the concentrations of all species? Now, in this case, we're trying to figure out the concentrations of each of these species at equilibrium, and we have this reaction. Once again, we draw an ice table, where we label the initial concentration, the changing concentration, and the equilibrium concentration. Let me tell you, Johnny, if you hadn't fallen asleep in class, I could have gone over this in much more detail, but because you fall asleep in class, I gotta spend this entire lunch doing it. And I don't have that much time, so you better not fall asleep in class in the future. Okay? I'm serious about that. Okay, so let's label our A, B, and C as the last time. Okay, so this is C, this is A, and this is B. What are the coefficients? 1, 1, 2. Okay, so our initial concentration, let's put each of these in. So H2, I2, and HI. Okay, so initially, these are both 0.75 m, 0.75 m, and this would be 0, because this isn't combined yet to become HI. Okay, now, oh yeah, one other thing I forgot to mention, the KEQ value is 6.3 times 10 to the power of 4. So let's just write down the equilibrium expression, which would be 6.3 times 10 to the power of 4 equals concentration of HI, and these are all gases, by the way, so keep that in mind, raised to the second power, divide that by the concentration of H2 times the concentration of I2. So that's our equilibrium expression, right there. Now, since these have a coefficient of 1 and this has a coefficient of 2, we know this is going to go down x. We don't know how much it's going to go down by, but it's going to be x. This is going to be plus 2x because there's a coefficient of 2 there. So now we can substitute these values into it to become 6.3 times 10 to the power of 4 equals, it would be 2x squared, 2x to the power of 2, over 0.75 minus x squared. And this one's squared just because there's 2 of them, so you can just combine them to become 0.7 minus x squared. So there's that. So now, how do we solve from this mathematically? Well, let me think here. Johnny, what do you think you would do? From your math classes, what have you learned from algebra to solve this question? Maybe you could take the square root of both sides, because they both have power 2. Exactly. Smart thinking, Johnny. Smart thinking. Take the square root of both sides, and it'll take away the squared in the fraction. And that will become 2.5 times 10 squared, Square root of that is 2.5 times 10 squared. And then that'll remove the square part of each of these to become 2x over 0.75 minus x. There we go. Now we can multiply, well, we want to get x alone, so we can multiply the denominator to both sides. So let's multiply both sides by 0.75 minus x. Multiply this side by 0.75 minus x. These will cancel, right? And that will become 2.5 times 10 squared is actually just 250. So it'll be 250, and then 0.75 minus x equals, what does that equal? That equals 2x. Now, Johnny, what would we do next? From your math classes, what have you learned? Distributive property? Exactly. Distribute this to each term in the bracket. So 250 times 0.75 is 187.5 minus 250x, because we're multiplying a negative by a positive, minus 250x equals 2x. Okay, so Johnny, what do we do next from your math classes? Combine like terms, move the x term over the 250x. Exactly right. Let's add 250x to both sides. 250x. This will become 187.5 equals 252x. Now, Johnny, what do we do next? Divide both sides by 252. Exactly. That'll get x alone. Divide both sides by 252. And that should give us x equals 0.744. And now we look back at the ICE table. We have this concentration minus x. So we take 0.75 minus 0.744, which should equal 0.01 m. These are both the same, so that's also 0.01 m. This is a bit of a rounded value, but yeah. And then 0m plus 2x would equal 1.48 m, because you take x and multiply it by 2. And there's the concentrations of each of the species at equilibrium. So as you can see, we had a lot of H2 and I2 and had no HI whatsoever. But when it gets to equilibrium, we have such a small amount of HI, H and I, and a huge amount of HI. And that is equilibrium for you in just over half an hour. Lunch break's going to end soon. I wish you were in class though, because I could have gone over this in so much more detail. But I had to keep the time limited here. Come back tomorrow for acids and bases. Glad to see you here today. But that's all it is to equilibrium. And remember, you are always equal. Farewell.